Hello, my name is Andreas René Geist, and in this video I will give a brief overview to our paper on Gauss principle adhering Gaussian processes. For the control of mechanical systems, we often desire a dynamics model of the system. That is, we require a function that predicts the next state of the system given state control pairs xk. Here q denotes the generalized position, q dot the generalized velocity, and u the control input at discrete time k. Given measurements y, such a function can be approximated via data-driven models. However, data-driven models are often not very data efficient. Alternatively, one can model the system's acceleration q double dot and combine such a model with a numerical integration scheme. The acceleration of a rigid body system can be approximated using analytical models. Yet analytical models are often underparameterized, which motivates the combination with data-driven modeling approaches. In this paper, we use the Udvardia-Calabre equation to linearly transform a Gaussian process model. Here, we leverage a priori available knowledge about the constraints and inertia matrix of the system to perform inference in a latent manifold of the acceleration space. In the following, I will illustrate how constraint knowledge provides useful structure for improving the data efficiency and physical integrity of a data-driven dynamics model. In analytical mechanics, the function for the acceleration of a rigid mechanical system is given via a generalized inertia matrix M and a generalized force vector F. The structure we use in our work to model the forces F are constraint equations. Constraint equations can be holonomic, such as the rod of a pendulum, or non-holonomic, such as the wheel of a unicycle. Constraints apply constraint forces Fc and in return change the system's acceleration. To understand how constraint forces and constraint equations are related to each other, one can take the first or second time derivative of constraints to obtain the constraining equation. For many interesting mechanical systems, the constraining equation is linear in the accelerations. Note that the forces of A would cause the acceleration vector A if there would be no constraints. The constraint forces Fc changes the vector A through the acceleration vectors tau ideal and z. It is D'Alembert's principle that tells us that tau ideal denotes a change in the acceleration that is directly caused by the constraints and which can be uniquely determined using Gauss' principle. In contrary, the acceleration z cannot be determined a priori using the constraint equation. These two principles give rise to the Udvardia-Calabre equation. Now the Udvardia-Calabre equation defines the system's acceleration as a function of the latent accelerations a and z. Here a denotes the unconstrained acceleration of the system and z denotes the change in the acceleration due to non-ideal constraint forces such as friction or damping. In the Udvardia-Calabre equation, the matrices L and T yield projections into the range space of the Moore-Penrose inverse of capital A and the null space of capital A, respectively. To obtain a probabilistic model for q double dot, we place the GP prior on the latent accelerations a plus z. As Gaussian processes are closed under linear operators, we obtain a Gaussian process posterior for the system's acceleration. Note that for the covariance function of the Gaussian process we can choose any positive definite kernel. The GP's hyperparameters are estimated jointly via type 2 maximum likelihood estimation. If no knowledge about A and Z is available, we can set the GP's mean mu to be a zero vector. Alternatively, the GP's prior mean can model the system's unconstrained acceleration using, for example, the Lagrange equations. Lastly, I will give a brief intuition on the predictions made by the Gauss principle adhering Gaussian process. Assume we want to predict the unicycle's acceleration q double dot 1 over a change in the angle q3. Here, to plot the GP's prediction in 2 dimensions, we fix the state space slice at which the angular velocity amounts to 0 and the translational velocity is greater 0. In the plot on the left, the x-axis denotes the angle q3 and the y-axis depicts the system's acceleration q double dot 1. We obtained the following plot by drawing samples from a Gauss principle adhering Gaussian process. In this figure, the real unicycle's acceleration q double dot 1 is depicted in black. The prior samples drawn from the structure GP are denoted in light blue and its posterior samples after conditioning on observations y in dark blue. Note that the mean and samples of the Gauss principle adhering Gaussian process fulfill the constraining equation by design. Thanks for watching. If you're interested in our work, please also have a look at the supplementary material linked in the description. You'll find our code on GitHub. If you have any questions, please don't hesitate to write me a mail.